Yeah, this is the fifth, I believe, in the series of videos that I'm making on second order systems and the step response of second order systems. uh, so where we are now, there's a few things left to clean up behind us, but I'll do that later. I want to show how to make a model of a second order system in Modelica. Actually, the other thing that I think I'm going to do, because it's very easy to do, is to show how to really do the same thing in another open source program called Octave, which is like MATLAB. So I'll do both. I don't know whether it'll probably take 2 videos to do this, so we'll see. What I thought would be a good exercise, actually, would be to actually make a model of this underdamped second order system from the response. So the scenario here in real life would be that we've run a test on a system and we've gotten a step response test on a system and we've gotten a response like this, and now we want to come up with the performance parameters for this system. We know, so the performance parameters are K, zeta, and omega n, and we know that what K affects the jump here as well, it's just what happens. Zeta affects the overshoot, and then zeta and omega n together affect the frequency of oscillation. So what we need to do is analyze this and figure out how we come up with a transfer function. And really, well, the gain is easy. Now, this is a problem we're making up here, and no one said, I don't believe it says it in the text, that this response was caused by a unit step input. But you need to know the size of the input step, and what we'll do is we'll assume that it was a unit step. So the input that created this was going from 0 to 1, and that produced an overall jump from 0 to 3 ultimately in the steady state. So that would mean that K is 3. Actually, I think I have some notes on this. Let me go back to my Word file here. Let's go down below. So, like I said, if the system's input is a unit step, then its gain is 3. So that's one of the 3 parameters we need, and that was an easy one to get. Now the system's overshoot is if we look at it, let me get it this back from behind here a bit. Yeah, that's good enough. The jump ultimately in the steady state is from 0 to 3. But it initially jumps up to what looks like about 4.6. So what we need is the percent overshoot, because the percent overshoot is what determines the zeta, or zeta determines the percent overshoot, actually, if I want to say it from a correct causal standpoint. So I started working this out, and then I thought, well, you know, I want to use Octave to do this. Octave, like I said, is we have, of course, in the commercial realm, the simulation packages that are most used commercially are MATLAB and Simulink, but there's good open source alternatives to these, and so my book focuses on MATLAB Simulink, but I would prefer to show how to do these with open source programs, because there are many places that do not have MATLAB and Simulink, which can be quite expensive, and the open source programs are actually cost-free. So I'm going to use Octave, which is like MATLAB, to do my calculations, and the first thing that I need to calculate is I need to calculate the percent overshoot, and here's my formula for it. So and you see where this number came from. 1.6 is the height from here to here, because it goes to 4.6, and you subtract the 3 off, and then I divide by 3 to get the percent overshoot. So I go to Octave. Octave can be downloaded for free. Just look for Octave or GNU Octave, and you wind up with something like this. So I'm going to calculate the percent overshoot. Percent overshoot equals 1.6 divided by 3. So I have about a 53.3333. That is the amount of overshoot I have, so 53.333%. Now I can calculate my overshoot from that percentage, and the formula for that, let me go back to my book. If we go down, here's the formula that relates zeta with percent overshoot. But we know percent overshoot, and now we want to get zeta. So what we do is we actually use this formula here, and let me get this where I can see it. So when I type it into Octave, I can be looking at both of them at the same time. One thing that's a curiosity between in both MATLAB and Octave is that there's no ln function. Okay, so like for instance, if I type in ln and then I put in PCOS, I get an error. There's no ln function. Unfortunately, I wish there were. So what they use instead is they use log for the ln, and then they use log 10 for the base 10 logarithm. And you can see that because if I put in log 10, no, that's okay, and then put in a 10. Remember what the logarithm is. The logarithm of this number is the power that you raise 10 to get that number. Now I raised 10 to the 1 to get that number. So the result of this, if log 10 is the correct function to use, should be 1. And it is. So log 10 gives us our base 10 logs, and log gives us what normally is ln. You can actually prove this too. Well, I'm just going to continue on. I don't want to get into a little, I don't want to get sidetracked here. So if I want to put this formula in, I want to calculate zeta, and it's equal to log, and then PCOS. Actually, it's a negative, so I can go back and put a negative sign in front of that log. Divided by SQRT, which is the square root, pi squared, and Octave knows what pi is, so we don't need to put in 3.1416, plus, and then we have our log. Well, we're going to need some parentheses to be able to square it. So now we put in log, and it is PCOS. Now everything has to be in the proper case too, because both MATLAB and Simulink are case sensitive. So there's our formula there for zeta, and if we hit enter, it says that our zeta is 0.19620, which is pretty light. We're a fifth of the way from no damping to critical damping. Now we need omega n. We have zeta, so that means we should be able to get omega n. And let's go and see where we get that from. Up here before, there was a relationship. Was it up here? No, I think it's below. Oops. Yeah, must be under here. Yeah, here we go. Here's our relationship between omega d and omega n. And we do know zeta. We figured it out from the overshoot. So I can solve this equation for omega n. I've got to get omega d, though. Now, omega d, as we talked about before, if we look down at the peak time has this relationship right here. The time it takes to get to the peak from the start of the step is pi over omega d. So we can measure the peak time, and then from that peak time we should be able to calculate omega d. So we just swap the places of these two, and omega d is equal to pi divided by the peak time. So let's go and look at our figure again. And the peak time, if we look at it, is about I would say 0.65 or so. Let's use that. So our peak time is that, and our formula, we're going to find omega d from pi divided by the peak time, which is 0.65 seconds. Yes. So we go back to Octave. We're looking for omega d is equal to pi divided by the time it takes to get to the peak. Okay, so that's our omega d, and with the omega d we should be able to calculate omega n. So if we come and we look back at our formulas again, yes, now we know zeta, we know omega d, so we can calculate omega n. So omega n is omega d divided by this. So let's put this up here so we can look at that while we're putting it in Octave. So omega n equals omega d divided by SQRT 1 minus zeta squared. Okay, that looks right. And notice that if we compare these two numbers, omega d and omega n, omega n is greater than omega d. So what that means is that the damped system is a little bit slower than the undamped system. The system would oscillate at omega n if it had no damping, but with the damping it oscillates at a little bit slower. Now with those, actually we can form the transfer function. We have k, I haven't assigned k yet, k is equal to 3, we determine that. So now we have our three parameters. We have k, we have zeta, and we have omega n. And we can actually make this transfer function for this system because we know, well, we have a formula for the transfer function. Actually, what I'm going to do is I'm going to stop here because it's a little place we can stop and the video is already getting a little bit long. So I'll come back in a minute and we will continue with this and form our transfer function.